Level 0. A grain of dust just died above your head, not metaphorically. Atom by atom, stripped apart by friction with the outer edge of the atmosphere, gone before it ever reached the ground. No alarm goes off when this happens. No agency tracks it. The sky simply absorbs it and moves on, like it's nothing. Around 91 tons of cosmic dust and debris enters Earth's atmosphere every day, yet most people never realize it's happening. Micrometeoroids hit the upper atmosphere at 64 kilometers per second, fast enough to make a rifle round look sluggish, and vaporize almost on contact. Scientists have found proof of this bombardment in Antarctic ice cores and deep ocean sediment. Microscopic melted spherules, the fossilized ash of debris that arrived and disappeared without a witness. Earth has absorbed this for 4.5 billion years straight, and it barely leaves a scar. But barely only holds at this size, somewhere above the point where objects stop vaporizing and start arriving intact. Level 1. The Sun looks calm from 150 million kilometers away, a steady disk, the same today as yesterday. That calm is a trick of distance. On its actual surface, the Sun releases bursts of energy called solar flares, and even the weakest classified category, C-class, already carries the force of millions of hydrogen bombs at once. Humanity built its entire idea of a normal day around a star quietly doing that on repeat. The classification scale A, B, C, M, X isn't evenly spaced. Each letter jump is roughly a tenfold increase in energy, so an X-class flare isn't 10 times stronger than a C-class. It's closer to 1,000 times stronger. Most ordinary flares just knock out a radio channel near the poles for a few minutes. Forgettable. That's the baseline. The historical record shows exactly what happens when the Sun stops behaving normally. And it happened long before we were prepared for it. Level 2. September 1859. A British astronomer named Richard Carrington was sketching sunspots when the Sun produced a blinding flash of white light, lasting only minutes. What followed reached Earth in under 18 hours, faster than almost any storm recorded since. Telegraph lines across Europe and North America caught fire. Operators reported electric shocks running through their equipment, some strong enough to keep sending messages with the batteries disconnected. Auroras normally confined to the poles were reported as far south as the Caribbean, bright enough that people reportedly read newspapers outdoors at 1 in the morning. Routine solar flares are one thing. This isn't routine anymore. Scientists now use Carrington as the benchmark for an extreme geomagnetic storm, and it isn't even the biggest one on record. Carbon isotopes trapped in ancient tree rings point to at least 2 far larger storms, one around the year 774 and another near 993, both believed to be associated with solar events even more energetic than Carrington's. Carrington happened before humanity depended on electricity for anything. Researchers estimate a storm of equal strength today could cost trillions of dollars, with recovery in some regions measured in years. We've had a close call since. In July 2012, a storm of comparable strength crossed Earth's exact orbital position, missing us by roughly 9 days. The Sun has already shown us it's capable of far more than Carrington alone. The only unresolved variable is timing, and timing is the one thing nobody on this planet controls. Level 3. The Sun at least gives warning. Sunspots build for days before a major flare. Not everything extreme announces itself that way. Some of it arrives from the dark with zero buildup, and only reveals itself once it's already close. Thousands of near-Earth objects are tracked today, their orbits modeled years ahead of time. Agencies rank the real threats on the Torino scale from 0, no hazard at all, up to 10, a certain global catastrophe. Almost everything ever tracked sits at 0. The system does have one persistent blind spot, though. Anything approaching from the direction of the Sun is nearly impossible for ground telescopes to see. That blind spot is exactly how, in February 2013, an object roughly 20 meters wide slipped past every warning system on the planet and entered the atmosphere over Chelyabinsk, Russia, undetected until it was already burning. It exploded roughly 29 kilometers up with a force near 500 kilotons, more than 20 times the energy of Hiroshima. The shockwave shattered windows across 6 cities, injuring over 1,500 people. Nobody saw it coming. The object capable of leveling an entire city isn't dramatically larger than that one. This one we only understood after the fact. What does the next one look like? And will the sky give us any warning before it arrives? Level 4. Step back far enough from asteroids and solar tantrums, and the scale changes entirely. Some events don't threaten a city. They rewrite what the night sky looks like for the next 1,000 years. In 1054, Chinese astronomers recorded a guest star bright enough to be seen in daylight for over 3 weeks, and at night for nearly 2 years. We know now what they saw. A star roughly 6,000 light-years away ran out of fuel and detonated as a supernova, briefly outshining every other star in the galaxy as seen from Earth. The wreckage, the Crab Nebula, is still expanding today. A supernova happens when a star finally loses a fight it's had with gravity for its entire existence. The instant fusion can no longer hold the balance, that balance collapses in seconds, and the rebound produces an explosion so bright it can briefly rival the combined light of its entire host galaxy. The nearest candidate within genuine range is Betelgeuse, roughly 640 light-years away, nearing the end of its life on a timeline that could mean tomorrow or 100,000 years from now. When it goes, it will be visible in daylight, brighter than the full moon. It poses no danger to us. It's simply too far. Distance is the only thing keeping a supernova filed under spectacle instead of extinction event. And there's a version of stellar death that doesn't need to be close to do damage. Level 5. Around 440 million years ago, something wiped out an estimated 85% of marine species on Earth. For a long time, the explanations were the usual ones: ice ages, sea level collapse. There's another hypothesis now still debated, and it doesn't come from this planet. Something may have arrived from deep space and done its damage in seconds. The suspect is a gamma-ray burst, the most energetic explosion confirmed anywhere in the universe since the Big Bang itself. In seconds, a single burst can release more energy than the sun produces across its entire 10 billion-year lifetime. We detect one almost every day, and nearly all are so distant they're just a data point, a curiosity rather than a threat. Almost all of them. A gamma-ray burst doesn't radiate evenly like a supernova. It's a focused beam fired from the poles of a collapsing star or colliding neutron stars, which is exactly what makes one dangerous if it happens to be aimed at you. The proposed mechanism for that extinction isn't the burst cooking the surface directly. It's subtler. A close enough burst could strip away Earth's ozone layer within seconds, exposing the surface to radiation for years, long enough to collapse food chains from the bottom up. No known star capable of this is currently aimed at Earth from close enough to matter. But we can't always know which stars are pointed at us until the beam has already left, meaning a threat like this could arrive with functionally zero warning. Level 6. In 2011, a telescope pointed at a distant galaxy caught something suddenly flare with the brightness of billions of suns. Nothing had exploded. No star had gone supernova. Something at the center of that galaxy had simply reached out and pulled a star apart. Black holes spent most of the 20th century treated as a mathematical curiosity that few theorists believed actually existed. Then we started finding them, not by seeing them directly, but by watching how everything nearby behaves as if it's circling a drain. That 2011 flare is a tidal disruption event. When an object strays too close to a supermassive black hole, the pull between its near side and far side becomes so extreme, it gets stretched into a stream of superheated plasma before it ever crosses the event horizon. A supernova needs to detonate. A gamma-ray burst needs to fire directly at you. A black hole doesn't need to explode or fire a beam across the universe. It only needs something to wander too close. Nothing needs to fall in. Nothing needs to cross the horizon. Proximity alone is the weapon. And there's a version of this violence that requires no black hole at all, just two dead stars, and a collision powerful enough to shake space itself. Level 7. Every gold atom you've ever seen, every ring, every coin, every wire inside your phone, was almost certainly forged before the sun ever existed, in an explosion violent enough to warp space itself. We are, quite literally, wearing the leftover debris of dead stars crashing into each other. On August 17th, 2017, instruments on opposite sides of the planet detected something arrive within the same 1.7-second window. Gravitational waves, ripples that physically stretch and compress space, followed almost instantly by a burst of gamma rays. For the first time in recorded history, the same cosmic event had been witnessed through two separate channels, gravity and light, confirming each other. The source was two neutron stars, city-sized remnants so dense that a teaspoon of their material would weigh close to 1 billion tons, colliding roughly 130 million light-years away. The resulting kilonova did something no supernova can. It flung outward several times Earth's mass in pure gold and platinum, seeding space with the raw material of future planets. That same event confirmed gravitational waves genuinely travel at the same speed as light, passing through every atom in your body for a fraction of a second, at a scale far too small to notice. We now know the universe itself can shake. Space isn't just the stage where cosmic events happen. Sometimes it's part of the explosion. And that raises a harder question. What happens at the absolute outer edge of what's physically possible? Not just violent, fundamental. Level 8. There's a hypothesis in physics that rarely leaves academic papers, mostly because there's nothing comforting inside it. It's called false vacuum decay. The universe we occupy might not be sitting in its lowest, most stable energy state. It could be resting in a false floor, stable enough to have lasted 13.8 billion years, but not as stable as it's physically capable of being. If that's true, a random quantum fluctuation could tip a tiny region of space into the genuinely stable, lower energy state. The new state wouldn't stay contained. It would expand outward at the speed of light, rewriting the fundamental rules of physics as it travels, potentially under conditions where atoms and matter as we understand them simply couldn't hold together. If this occurred somewhere in the universe right now, close enough that the boundary was heading our way, there would be no warning whatsoever. It moves as fast as light does. The edge would arrive at the exact same instant its light did. Nothing would appear in the sky first. Nothing would give you time to notice. This remains firmly speculative, studied by physicists working on the implications of the Higgs field, not a predicted event. Most researchers consider it either extraordinarily unlikely or effectively impossible within any span of time worth worrying about. But it sits there anyway, at the very top of everything physics currently allows us to imagine, which means this might not be the final level. It may simply be the highest one our understanding has managed to reach so far.